In this lesson, we're going to talk about propagating uncertainties by hand. Now, so far in this course, we've said if you want to work out the uncertainty in something, just use Python or some equation. Someone else has done it for you, which is much easier. So why would you ever bother doing it yourself? Well, mostly it's so you can get an equation for the uncertainties. If you actually have an equation, this is a total uncertainty, it tells you what it depends on. And that can be really important. For example, for telescopes, you can see that the sensitivity depends on the diameter squared. So it means you really want a big telescope. Or maybe you find that the gravity wave uncertainty is mostly dominated by vibrations in your mirror, so you have to work really hard at making the mirror better and don't worry about some of the other things. So these sort of equations can really tell you where the uncertainty is coming from, what things you have to do to make things better. So that's the main reason why you need to do this.
Some terminology. If we have a variable x, then we're going to write the uncertainty in x as sigma x. Note that the equations we're going to show you only work if sigma x is quite a bit less than x. So for example, if the mass of something is 10 kilograms plus or minus 1, that's okay. But if it was 10 kilograms plus or minus 1,000, that wouldn't be okay. If the uncertainties are really large, you actually have to do a numerical simulation to handle them. So all this works where the uncertainty is less than the actual value. Okay, now the fundamental principle is one from calculus. Let's imagine you have some variable x, which has some uncertainty, sigma x, and you want to know what effect it has on y, and what's the uncertainty in y. Now, if x equals y, then if you have a particular value of x with a particular uncertainty, you can just go up here, that uncertainty range, which correlates to that uncertainty range, so we end up with the value of y and uncertainty in y. All very straightforward, they'd both be the same. But if the graph is not a straight line, let's say it starts flat and then goes steep. Now if you have a value of x down here with a particular uncertainty, that might mean you're going to be somewhere between there and there, but that actually gives you only a very narrow range of values of y. So in this case the uncertainty in y is very small, even though the uncertainty in x is quite big. If on the other hand you're up here and you've got an uncertainty, that means you're going to be somewhere between there and here, which is an enormous range in y. So what this means is if the slope of the graph is steep, then a small uncertainty in x produces a big uncertainty in y. If the slope is flat, then a small uncertainty in x produces a tiny uncertainty in y. To do it mathematically, we've got that y equals some function of x. We can work out dy by dx, the slope, which can be also written as like f prime of x. This tells us how much y responds to a change in x. So the fundamental equation for this is that the sigma in y equals dy by dx times the sigma in x. You can basically think of sigma x as a small amount of x, so that's like a dx, so the dx's cancel out and you get the dy equals dy. And this is the fundamental equation behind all uncertainty propagation.